bandwidth? So what is the highest gain? Is minus 2.8, right? And corresponding frequency is 23.1. Are you all following or not?
Yes, sir.
So last class we did this band pass filter and we measured the bandwidth of the filter. And what is the cutoff frequency, design cutoff frequency? That is resonant frequency. I'm asking resonant frequency. What is the resonant frequency? According to the theoretical calculation. You have that PPT or not? Okay, I'll show you the this was the last class question, right? Yes or no? This is the last. I asked you to design a band pass filter in LT Spice for this values. So for this value, what is the bandwidth? The band that is resonant frequency is 23.2 kilohertz, right? And bandwidth is 1.6 kilohertz. The same thing can be found in the graph. So the resonant frequency is 23.2 approximately, and the maximum gain is minus 2.2. So what is minus 3 dB? Minus 2.2 minus 3. How much? How much at 3 dB? Minus 2.2 minus 3 is how much? Minus 5.2, right? So you have to place the cursor at minus 5.2. So this is minus 5.2. So F1 is 22.9. So what is the F2? So F2 is 23.5. So the bandwidth is how much is coming? Practical bandwidth. Anyone who verified it or not? Please say something. You verified it or not?
No, sir.
Sir, actually, in
Now
class, the graph didn't come out correctly, sir. So you told in this class you would be explaining it again.
So now you got this graph or not? You have the same circuit? You have the circuit?
Yes, sir.
So this is the circuit, right? This is the circuit, right? This is the last circuit, and this is the. Have you set these values for inductance, capacitance, and resistance, and
Yes,
voltage?
sir.
So next thing is you have to simulate it, and you can see the graph. So this is the graph. All of you are getting this graph or not?
Yes, sir.
And you can zoom it, and you can see the values of x-axis, y-axis right below the left corner. That is here you can see the x-axis, y-axis values. So what is the highest gain now? Highest gain is minus 2.338 dB, and corresponding frequency is 23.0, which is same as our theoretical calculation, right? Yes or no? So theoretically, we found the resonant frequency of 23.2. Same values coming, right?
Yes, sir.
So 23.2. What happened? It's running. Keep on. So at peak value, at peak it's 23.2 minus 2.4, and you can, so 2.4 minus 3 is 5.2 approximately. So at 5.2, 5.28, it's 22.3. And similarly, at F2 is 24. So approximately it's coming 1.6, right? The bandwidth. Yes or no? Are you getting the same values as per the theoretical calculations?
Yes, sir.
Okay. So we can plot the frequency response in LT spice, and we can find the bandwidth, practical bandwidth of the filter. So this band pass, band stop filters are very useful in communication receivers to select the particular stations. So we can construct the band pass filter using a simple RLC element using the resonance property of the RLC element. So this is band pass. If you want to construct a band stop filter, just you have to do the reverse process. That is, this is series circuit. You have to make the parallel circuit. So we can design a band pass and band stop filters. So that's all about the uh, basics or fundamentals of this course. So I given an introduction to some measurements of the measurements, and we also constructed some simple circuits and verified the voltages and currents with the theoretical calculations. Next, we move on to the actual experiment. So our first experiment is to plot the VA characteristics of the diode. So diode is discussed in the class. I think most of you are aware of diode, right? Shall we do diode? Diode characteristics. What is a diode? What is the property of diode? Anyone, please? Characteristics of diode is discussed in the class.
Sir, it conducts electricity in one direction.
So it conducts electricity electricity in one directions. What is depletion region? What is depletion region?
Sir, it's the middle point of the PN junction where the charges meet.
Yes, charges at the room temperature. Some of the electrons in the end region crosses the junction and combine with the holes, and similarly the holes near to the junction combines with the electrons in the P region. This process will continue until barrier potential is formed. So this barrier potential for the diode made up of silicon is 0.7, and diode made up of germanium is 0.3. And I'll show you the VA characteristics of diode. Some of you are there in my theory class, or no one is there from my theory class.
Not in the theory class, sir.
So no one is there in the theory class, right?
No, sir.
Anybody is there? The theory class. So this is the p-n junction formation. This is the p-n junction. Half of the silicon material is doped with the p-type region, and half of the semiconductor is doped with the n region. So the when junction is formed, room temperature, some of the electrons near the junction will cross the junction and diffuse into the holes, combined with the holes in the n region, that is p region. Similarly, some of the holes in the p region combines with the electrons in the n region. And this process will continue until the barrier potential is created. So you can see the positive ions and negative ions at the across the junction. So this prevents the further flow of electrons and holes through the region. So at forward diode will conduct only if the applied potential is greater than points above 0.7 volt. That is for silicon, and this is for the germanium. And this is the depletion region. This is the depletion region and forward bias characteristics of the diode. And this is the forward characteristics of the diode. So as you can see, there is a little forward current for a forward bias below barrier potential. So there is little forward current for the forward voltage below the barrier potential. As the forward voltage approaches the value of barrier potential, the current begins to increase. So the current begins to increase. Once the forward reaches the barrier potential, current decreases drastically. So you can see the drastic increase in the current. So we are going to plot the same characteristics in the LT spice. Okay. So we can construct a circuit. Let us take the simple circuit. And you can use a diode. Now circuit is done, right? Have you all constructed the circuit?
Okay, wait 1 minute.
And DC voltage, you have to set it as 5 volt. This is 10. You can give a resistor value of even you can change it to 1K. Then
So what's the diode value?
diode is 1N. Diode is 1N4148. 1N4148. Once done, tell me. Yes, finished. Finished. So next we can simulate it.
Sir, once can you show how to enter values for the diode, sir?
I'll tell you. Diode, just you have to click it and pick new diode. You have to select IN4148. Give OK. That's it. So all the values are now defined, right? resistor value is defined, and input power supply is defined, and diode type of diode is also defined, right? Then next you can simulate it. So in simulation, edit simulation command. So use DC sweep. DC sweep. Name of the source. Name of the source is V1, right? Name of the source is V1. Start value 0. Stop value some 4 volt or 5 volt. Increment in the size of 1. And if you place this what is the source name? V1. Okay, DC.
Sir, how to get the DC sweep, sir?
So simulate. Go to simulation setting.
Okay, sir.
You can V1. So name of the first source to sweep is V1, and type of sweep is linear. Start value 0. Stop value 5 volt. Increment 1.
So what's the value given for the diode, sir? Can you please repeat that?
Diode type is 1418.
Okay, sir. Thank you.
Now are you able to see the output? And if you want to, y-axis is current. So this is y-axis current. Are you able to see the graph? So after 0.7, you can see the sharp rise in the current.
Yes, sir. Yes.
Yes, sir.
So this is how you can plot the characteristics of the diode. And this is for the forward characteristics. And can you do reverse characteristics just by changing the direction of diode? So you can change the direction of diode and you can see the graph of the reverse bias. So try to do it, and if you have any problem, I'll help you.
Sir, excuse me, sir.
Yes.
Sir, can you once again tell how to get that tran of 1M and DCV1051?
Yeah, after simulation, it transient response, that is transient response. So this is the VA characteristics, and you want to volt transient analysis. Tran means transient analysis, and transient analysis is for 1 milliseconds. I think okay. Linear increment value 1. So what is this 1 millisecond 1 m?
Sir, how to set the transient values, sir?
Transient values are not required. I'll simulate, go to the simulation settings, edit simulation command, and DC sweep. DC sweep. So DC sweep V1, name of the source is V1, and type of sweep is linear. Start value 0, stop value 5, and increment in steps of 1. Same thing is coming for all 1M.
Sir, if we are doing DC sweep, only DC one is showing. We are not getting trans 1M. Is it fine?
Trans 1M is not required. I don't know why is coming like this.
Sir, maybe you have done transient analysis at first.
Yes, because of this one. Could not even remove it now. I can't even. Ah, yes, now it's removed. Let us see. Again, it's coming. Oh, now it's not coming. Yes, it's earlier one. Now forward bias is fine. Yes, it's fine. All are getting the same graph and circuit diagram.
Yes, sir.
Now do reverse bias and plot the graph.
So for the DC sweep, what is the start value?
DC sweep. Start value 0. 0 axis 0. Stop value 5 volt. Maximum value of x-axis, because we have given 5 volt, an increment in steps of 0.1, increment in steps of 3. Let us see what's happening.
So for me, the voltage is like opposite. So the graph is showing opposite, but with the same values though.
Where you have connected the probe. Probe should be connected to the output end. That is across the resistor.
I'll check it 1 second.
All of you do the reverse bias. So I'll show you the graph for the reverse bias.
Sir, diode value is same.
Diode value is same. The output current varies in picoampere. You can see the y-axis output current now varies in picoampere. So this is the reverse bias characteristics of the diode. No current flows through the diode. Diode is act as a open switch. So the equivalent circuit of the reverse bias condition is open switch, and equivalent circuit of forward bias is closed switch. Got it?
Hello, sir.
Yes.
Sir, my graph is coming a bit different.
Can you share the screen? I'll tell you. What's your?
And sir, Chandok Das, sir.
Spell your name.
Sir, it is CHH.
OC, so OCHH.
Yes, sir.
Yes, now you can share the screen.
So can you see my screen?
Yes, loading. Screen is not visible.
Can you see it now?
No.
I think, sir, he's getting a slant line instead of a straight line.
Yes, let us see. Wait. Okay, he has done the simulation. 1K resistor DC V1 0 5. What is this one?
So one increment value.
Okay, increment value. Okay, and corrected simulated. Oh, you are getting the graph like this for the reverse bias or for the reverse bias.
Yes, sir.
Edit simulation. Go to edit simulation. I want to see the settings. I think settings are correct only. DC, go to DC sweep. Okay, V1 linear start value 0 5 1. Okay, okay, give okay. And simulate it again. The resistor is connected. Okay, simulate it again. Okay, next you connect the probe. Why is graph is coming like this?
Sir, I'm also getting the same thing, sir.
Yes, sir.
Yes, sir, even I am.
But output current varies in microampere. For me, why it's you change anything in the power supply? Power supply value same, right? DC
No,
supply.
sir. Everything, sir.
Huh?
DC is 5 volt. Yes, sir. DC is 5 volt.
Okay. Why I think we need to zoom something? 5 volt.
Sir, can you show your screen?
Yes, I'm okay. I'll. This is my screen. Okay, given in steps of 3.
It is not visible.
Increment of 1.
The screen is not visible. It's not visible now.
Yes, now it's visible.
Yes, sir.
Yes, sir. Now it's visible.
Okay. Now I am getting graph like this. Are you getting the same graph? Same graph is coming for you?
Yes, sir.
Okay. So all of you getting the same graph, right? For the settings. It is input power
Yes, sir.
supply is 5 volt, resistance value is 1K, and source is V1 and 0 to 5 volt with an increment of 1. So the so we have plotted the forward and reverse characteristics of the diode. Next.
You didn't seem to pick type of diode, sir.
Oh, sorry. Okay, that's the problem. Okay, now if I simulate it again. It again. Okay. So this is the voltage characteristics of diode, and this is the current characteristics, right? Same graph is
Yes,
coming.
sir.
Okay, okay.
Yes, sir.
Sorry, I didn't select the diode. So it's approximately same as that of your theoretical curve. So in microvolts, so the graph is after which it, so after breakdown only the current increases abruptly. So you can see from this graph, we are not operating the diode at breakdown point. We are operating just below the breakdown point of the diode. So the voltage is almost constant and current is almost constant. And once breakdown occurs, then current starts to increase. But uh, this operation, this condition should be avoided. Otherwise, diode will be damaged. We should not operate the diode and reverse breakdown point. So now the diode is done, right? Forward and reverse characteristics is completed. Next, what is the application of diode? Diode allows current in one direction. What is the use of this? So we need to convert the AC signal into a DC signal. So all your laptops and charger and mobile charger, all these devices are working on DC power supply. So what we get from the EB office is AC supply. So we need to convert the AC signal into a DC signal for most of the applications. So that is done by the circuit called rectifiers. So rectifiers are used to because of the ability to conduct current in one direction and block the current in other direction. Diodes are used in the circuits called rectifiers. So that converts the AC voltage into a DC voltage. So rectifiers are found in all power supplies that operate from AC voltage source. So all your laptop power supplies and mobile all operate from the AC voltage source, right? So we need to convert this AC signal into a DC signal. DC signal means so we can use the diode because a diode conducts only one directions, and you can see the operation of diode working of diode for the positive cycle and negative cycle. So negative cycle is completely there is no flow of current through the diode as you have studied the reverse bias characteristics of diode. So from the reverse bias you can observe that there is no current. You can observe no current during the reverse bias condition. So this is the forward characteristics. Forward characteristics of the this is the response of the circuit for the positive cycle of the input, and this is for the negative cycle of the input. No output because diode acts as an open switch. So output voltage across this resistor is 0. Can you simulate this circuit in the LT spice? You need an AC power supply, right? 230 volt, 50 hertz frequency. Can you try this in LT spice? Can you try? Can you try?
Yes, sir.
Circuit,
Okay.
exactly.
Connect this circuit and set the values of the power supply and resistance value. You can give it as 1K. Try to simulate it. Finished? Finished? Finished or not? Anyone? Finished? In power supply, you have to go to advanced. Advanced, so your input voltage is to 230 volt and have frequency is 50 hertz. And if you want to have some series resistance of the power supply, we can give point something, not 1. And so the input is given, resistance values are defined, diode is defined, and then you can simulate it. So you have to go to edit simulation. So transient analysis, transient analysis. Transient AC. Type of sweep is so type of sweep is linear. Number of points. Okay, this is AC and transient analysis. Stop time is give some 10 milliseconds or something. Okay. Next, simulate it. If you want to see the correct waveform, so edit simulation, stop time 100 milliseconds. Yes, are you getting this graph for the off-wave rectifier?
Yes, sir.
So this is for off-wave rectifier. So off-wave rectifier,
Yes, sir.
we have only one diode. So diode conducts during the positive cycle, and diode will act as an open circuit during the negative off cycles. So this graph is not a pure DC one, right? Right? How to get the pure DC signal at the output? So you can see the wave shape. Wave shape should be constant. That is DC is current and constant. So you have to filter this using a capacitor. So if you connect the capacitor across this, let us see the waveform. And you can use a capacitor value of say 100 microfarad, 100 U. Now you simulate it. You could see the difference with capacitor and without capacitor.
Yes.
Are you able to, so this is with the capacitor. So capacitor filter out the ripples in the AC signal. Output is not a pure AC. Output is not a pure DC. Output of the rectifier is not pure DC. So in order to get the pure DC signal at the output, we need some filter. So if we use any capacitor filter, so we can filter out the ripples. So let us increase the capacitance value to try for some other value. 100 microfarad, 1000 microfarad. So you can get almost steady state value, right? Constant voltage at the output, right? Using a capacitor. Got it?
Yes, sir.
So rectifiers with the filter gives the correct output. Rectifiers without filter will not give the correct output, and you have ripples in the output. So this is for half wave rectifier. Can you try full wave rectifier? So how to construct a full wave rectifier? I'll show you the block diagram. Two diodes. So one diode should conduct in for the positive cycle, the other diode should conduct in reverse during the negative cycle, right? So this is the full wave rectifier. So difference between full wave rectifier and half wave rectifier is that full wave rectifier allows unidirectional current to the load during entire cycle, and half wave rectifier allows only during the 1 hour of the cycle. So this is the major difference between half wave rectifier and full wave rectifier. So you have both cycles at the output. So how to obtain this? Okay, two diodes. Okay, what else is required? See, during the positive cycle, one diode should conduct, and during the negative cycle, other diode should conduct. How this happens? So you require some phase reversal between the diodes, right? So positive cycle is
Forward bias.
so if the two diodes receives the input signal with opposite phase, then for positive cycle one diode will conduct, and reverse for negative cycle the other diode will conduct. I'll show you. So you can use a center trap transformer. So center trap, if you apply a waveform through the center trap transformer, and the signal is coupled by mutual inductance, and you can see the waveform at the output of the upper half of the secondary and lower half of the secondary. So the upper half of the secondary and lower half of the secondary have 180 phase reversal. So during the positive cycle, the diode D1 will conduct, and during the negative cycle, diode D2 will conduct. So you can see the negative cycle is there is a 180 phase reversal for the positive cycle and negative cycle between these two half of the secondary. So using this property of the secondary trap transformer, so we can design a full day rectifier. So can you design a full day rectifier now? So if a transformer is not available, so you have to use three inductance. One inductance for the primary and two inductance for this secondary. You construct the circuit. I'll tell you how to set the values. You construct the same circuit I have shown now, and take three inductance, one inductance for the primary, the two inductance for the secondary. Can you try? Can you try this? Any doubt in this?
Sir, we're not sure, sir, but we'll give it a try.
Okay, so you take three inductance, one inductance for the primary and two inductance for the secondary. You construct the circuit, I'll tell you.
Sir, can you show us the previous circuit once?
This is the previous circuit.
Sir, how did you get that RSER? How did you
That
do
is
that?
internal resistance of the see the internal resistance of the power supply. 230 volt. That is a standard power supply from the office. So 230 volt and 50 hertz sine wave, and series resistance is 0.001. This is just for our convenience.
Okay, sir. Thank you.
Now do the full wave rectifier.
Sir, what was the value of the capacitor in the previous circuit?
100,000 microfarad. 1000 microfarad. It is 10,000 microfarad. Working on this full wave rectifier. Working on this.
Yes, sir.
circuit? Circuit is done. Circuit is done or not? Yes.
Yes, sir.
Okay. I'll show you
Sir, that
the.
inductor will we have to use the normal inductor, right?
I'll show you the normal inductor. I'll show you the circuit diagram. This is what the circuit for the full wave rectifier. So this is the circuit of full wave rectifier, and input is as usual 230 volt 50 hertz power supply, and you can give the series resistance of 0.001 milli ohm, and the L1 is value L1 value is 100 micro henry, L2 is 0.1 micro henry, and L3 is 0.1 micro henry. Both L1 and L2 are values are same. 100 micro henry, and diode D1, D2 are the same, IN 1N 4148, and resistance value is 1K. And so you have to take I'll show you how to construct the inductor like this. So take the inductor and press Control E to obtain the mirror image. So you have to do like this for this transformer, center trap transformer. Your circuit appears to be same as this. Yes. Your circuit is
No,
same as
sir.
that of this.
No, sir,
Yes.
I'm doing it now. Just a minute.
Okay. 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 I'll give you 5 minutes time. If you have any questions, you can ask me.
Done, sir.
So all the values are defined.
Yes, sir.
0.1 microhenry, 0.1 microhenry, and this is and you have to K capital L1, capital L2 like this in this this spice directive. So you have to type this K L1, L2, L3, 1. Have you done this? Have you done this?
Sir, how to name them?
So go to this spice directive. Spice directive, you can type this K, capital K, L1 space L2 space L3 space 1.
Done, sir.
Okay. So you can see the dot, the inductance. Now everything is made. Everything is made ready. So I'll show you the simulation. And this is the output of this circuit. Full wave rectifier. I got the. Are you getting the same waveform? Are you getting the same waveform? Like this?
Sir, what are we used in the place of inductor, sir?
We use only inductor. In place of transformers, we use inductance.
Sir, but I also used inductor, but I didn't get anything like this.
You have to set the spice. There is K, L1, L2, L3, 1 is coming.
No, sir. How
You
should I
have
do
to
that?
you have to go to this edit text on schematic, the last available at the last icon.
Okay, sir.
And you have to type K, same format, K, L1, L2, L3, 1. Anyone got it? Waveform, got this waveform?
Yes, sir.
Okay.
Yes, sir.
So this is the output of the full wave rectifier. We can improve the response by connecting a capacitance. So connect the capacitance across the resistor. So your response will be more smoothened out. So if you connect the capacitance across this, I'll take on capacitor and capacitance. Control R. Okay. Control R. Then connect this capacitor using. Now you can set the value of this capacitor. 100 micro, 1000 microfarad. Now you could see the result. So we'll get somewhat DC waveform. This is with the filter. Without filter, you will get ripples in the output. So done with filter, without filter.
Sir, how much you have entered for a capacitor?
1000 microfarad.
Okay, sir.
So we have done half wave rectifier, full wave rectifier. So you can also do the full wave rectifier using bridge circuit. So I'll show you the circuit diagram of the bridge rectifier. So for bridge rectifier, you don't require center tap transformer. Bridge rectifier is circuit. Okay, I'll show you the bridge rectifier circuit. All of you done the full rectifier?
Yes, sir.
Okay, next you do bridge rectifier.
Yes, sir.
I think you can see the get the circuit from the internet also. Anyway, I'll share the circuit diagram. So this is called known as bridge rectifier. Are you able to see the circuit diagram? Are you able to see the circuit diagram?
Yes, sir.
So this is called full wave bridge rectifier. So what is the advantage of this bridge rectifier is it eliminates the need of center trap transformer. For full wave rectification, you require transformers, three coils. But in case of bridge rectifiers, you can use as two coils, L1 and L2. Can you try this full bridge rectifier now? You require only two inductance, L1 and L2. Can you try this?
Yes, sir.
Okay, try. Can I construct the circuit and verify the result? This is the last part of this class. Completed. Meanwhile, I'll take attendance. All of you, please answer your attendance.
Sir, after we've given our attendance, can we leave the class, sir?
No, you have to complete this bridge rectifier. Bridge rectifier is completed, you can leave.
Okay, sir.
Today is L23, right? L23. This is L23
Yes.
lab. Okay, I take attendance. So please, all of you answer, unmute your microphone and give your attendance. Don't interrupt me before while taking attendance. So if you're not answered for attendance, we can give it later. So Amsika,
Present, sir.
Naman Kumar,
Present, sir.
Vivin,
Yes, sir.
Gokula Krishnan, Gokul Krishnan,
Present, sir.
Giridhar Prakash,
Present, sir.
Sahid Ahmad,
Yes, sir.
Ankita Das,
Present, sir.
Priyanshu,
Present, sir.
Aditya Sharma, Aditya Sharma, Abdul, Abdul, Abdul also absent. Tejas,
Present, sir.
Tejas,
Present, sir.
Pranav Arish,
Present, sir.
Nitin Reddy,
Present, sir.
Shankar Shai Prasad,
Present, sir.
Sri Rohit Chaudhary,
Present, sir.
Hariharan,
Present, sir.
Amal Vishnu,
Present,
Amal Vishnu,
Present, sir.
Ishan Saxena,
Present, sir.
Krishna Chaitanya,
Present, sir.
Suresh.
Present, sir.
Sir, present, sir.
So tell it later. Lauren.
Present, sir. Present, sir.
So Vishweshwar Reddy,
Present, sir.
Kanchana,
Present, sir.
Abhirami Bhaskar, Abhirami, Venkata Yogita,
Present, sir.
Ashit Kumar,
Present, sir.
Srinidhi,
Present, sir.
Jiva,
Present, sir.
Jiva, okay. Abhigyan Goshal,
Present, sir.
Yadu Krishnan,
Present, sir.
Rahul, Kevin,
Present, sir.
Vikramaditya, Subrato Dey,
Present, sir. Om Subrato.
Om Subrato Dey, Sanjay Ankit,
Present, sir.
Sai Venkatesh Varun,
So present, sir.
Ankit Singha,
Present, sir.
Kritika,
Present, sir.
Sriram Sai Manjunath,
Present, sir. Present, sir.
Bhavya Yadav,
Yes, sir.
Rishikesh, Mamit Singh,
Present, sir.
Siddharth,
Present, sir.
Nikunj Agarwal,
Present, sir.
Dhananjaya Reddy,
Present, sir.
Charan Rahul,
Present, sir.
Kirat Singh,
Present, sir.
Devansh Gupta,
Present, sir.
Rahul Prem,
Present, sir.
Devanathan,
Present, sir.
Sanjukta,
Present, sir.
Rangaraj,
Present, sir.
Stanley,
Present, sir. It's
Stanley.
Freddy. Yes, sir.
Okay.
Present.
Megha.
Present, sir.
Okay. Rishwant,
Present, sir.
Deepan.
Yes, sir.
Gopinath
Present, sir.
Who is present?
Deepan, sir.
Gopinath,
Present, sir.
Gopika,
Present, sir.
Jervin Matthew,
Present, sir.
Mohammed Salam, Salman, Muhammad Salman.
Present.
Okay, sorry. Arsh Dev,
Present, sir.
Gokul Raj,
Present, sir.
Sneha,
Present, sir.
Surya Deepan,
Present, sir.
Guru Prashad,
Present, sir.
Guru
Present,
Prashad, Mohammed Azim,
Present, sir.
Sindhu.
Present, sir.
Present, sir.
Okay, Muhammad Azim present. Okay, Sidhu present. Kapilan,
Present, sir.
Nitin,
Present, sir.
Maurya,
Present, sir.
Salav.
Present, sir.
Okay,
Sir.
Salav.
Yes,
And Chandak Das,
Present, sir.
Aditya Sharma, sir. Present, sir.
who is present? Tell me the correct register, full register number, because its class is mixed.
Sir, 21 BAI 1107.
You belong to which branch? BA, which branch?
AIML, sir.
Oh, AML. Okay. 21 BAI.
1107, sir. Aditya Sharma, sir.
Okay. AML. Okay.
Thank you, sir.
Anyone is marked absent wrongly? You can see the absentees list now. I'm scrolling, so you can see the absentees. So if anyone is present,
Sir, Vikramaditya.
Number, full register number, BAI or
21 BAI 1870.
one not 1070, right?
1870, sir.
So I'm going to close it now. I will not change it.
Sir, Amal Vishnu is present. I had a doubt whether I am absent or present. You have marked it.
What's your number?
21 BAI 1416.
Amal Vishnu present.
Thank you, sir.
So if you completed, you can leave. Got the output for this? Anyone got the output for this full bridge rectifier? Anyone got the output? Say yes or no?
Sir, it is showing that the secondary coil is not getting any voltage.
Can you share your screen?
Yes, sir. Please make me the presenter.
Name, what's your name? Naman.
Yes, sir.
Yes. You can show the circuit diagram now. So
Can you
four
see it, sir?
diodes. Yes, four diodes and two resistors, two inductance. And what you have to set the spice. That is here. You have to set the K L1 L2 1. You have only two inductance.
Oh
so
yeah,
K,
I have not done that. What was it, sir?
K space capital L1 space capital L2 space 1. Space K space.
Okay. Is it correct, sir? Just a minute.
Space, give space. Okay. Now we simulate it. Both are 100 micro Q 0.1 micro for the L2 because there won't be any step down action. 0.1 micro entry. Okay.
Yeah, now current is there.
Waveform is like this. Adjust the time period or something. Go to the simulation, edit simulation. What are the values you have given?
Sir, in transient, I have given stop time 100. That's it.
Stop time 100.
Sir, 100 milliseconds, sir.
Milliseconds, 100 milliseconds.
Okay.
Yes.
Yeah, it's coming.
Yes. Now it's coming. Can take the output across the resistor. So all of you have done this bridge rectifier.
Yes, sir.
So I'll upload the sample report format. So you have to maintain a soft copy of the for every lab Word file. The first class we did some resistor experiment, simple resistor circuits, and we also simulated a band pass filter in the first class. And the second class we did 3 experiments. That is diode characteristics, off wave rectifier, full wave rectifier, and also the bridge rectifier. So you maintain a Word file for this and having a circuit diagram and output waveforms. And I'll give you the format. You can modify this Word file accordingly. Okay.
Yes, sir.
So all of you can leave. So if you have any questions, you can stay back. Otherwise, you can leave.
Thank you, sir.
I'll wait for 2 minutes. So if you have any questions, you can ask me. Others can leave.
Hello, sir.
Yes.
Sir, all the circuits that has been done today, all of them are part of the lab.
Yes, all of the 3 part of this lab, today's lab. That is diode characteristics
Send the PPT and also some material. So we can.
Okay, I'll share it.
Also, if possible, send material. How do we like exemplar kind
Yes,
of thing?
Yes, I'll upload it. No, don't worry.
Okay, sir. Thank you, sir.
I'll upload it in Moodle. Sorry,
Moodle.
not in Moodle. Teams.
Yes, sir. Thank you, sir. And when do we have to submit it by next lab?
Not next lab. I'll create a link in the Moodle. You can upload it.
Moodle.
Yes. Yes. You have to submit only in the Moodle, not in Teams.
Okay, sir. And also one thing.
Yes. Tell me.
Sir, we have to handwritten it or make it in Word file.
The typed one. No need to handwrite. No need to.
Yes. Okay, sir. Thank you.
Thank you. So I'm leaving now. So thank you.
Thank you, sir.
Thank you.
Thank you.
Thank you.